Alright, so what you're looking at on the screen right now is, well, a teapot. Yeah, a good old classic teapot. But there is a little twist here. Most of the time, when you see a 3D model in a graphics demo like this, there is some kind of file behind it. For example, an OBJ or GLDF file. Something that sits on your disk and gets loaded at the startup. But in this case, there is no model file, nothing. The teapot you are seeing doesn't exist anywhere on my drive. Instead, all of its geometry, every vertex, every point, is created on the fly. The entire teapot is built out of multiple surfaces, also called patches. Each patch is basically a tiny little chunk of the surface. In this particular example, a single patch is made from a 4x4 grid of control points, so 16 points per patch. And here is where it gets fun. At runtime, the GPU generates more intermediate vertices and triangles using a mesh shader. So the teapot you're seeing isn't pre-baked. It's being generated right now, every frame, based entirely on these control points and the math behind them. You may ask, why mesh shaders? Why not, for example, a tessellation shader? Well, technically it's possible to use tessellation shader for this demo, but tessellation comes with quite a few limitations. Fixed pipeline stages, awkward control, and the physical limitation on the number of subdivisions. Mesh shaders, on the other hand, that's a pure compute beauty. You get full control over how the geometry is generated, how it's grouped, how many vertices or triangles you want. And the whole thing is incredibly flexible and efficient. So, in this series, we are going to build this entire application completely from scratch. We are doing everything in C++ and Vulkan. No shortcuts, no pre-made engines, no black boxes. We will walk through setting up the project, building the mesh shader pipeline, generating patches, creating surfaces, and eventually rendering the teapot exactly like you see here. If you're into the Vulkan, graphics programming, or just want to understand how modern GPUs actually work under the hood, you will enjoy this. Hello world, my name is Nikita Black and I'm happy to see you on my channel. As you probably guessed from the intro in this series, we will talk about mesh shaders. I personally like mesh shaders because of this unique mix of compute and graphics. So I think it's an amazing technology which touches to both the compute pipeline and the graphics pipeline. And the Vulkan is a great API to leverage this technology. So yeah, let's do it in Vulkan. In the beginning, I wanted to jump straight into the coding, into mesh shaders. But later I realized that if you take many different people and look at how they write Vulkan code, you probably will find that all people write the code differently. And I'm not an exclusion from this. And to avoid the questions why I decided to program like this, why I chose this direction, I decided to code the complete application entirely from scratch. Yeah, so we will not use any graphical third-party libraries. Instead, we will do everything completely from the empty file. Of course, we will use third-party libraries for things like window and some utilities, but the application itself will be fully written from the scratch and it should be cross-platform. I will write the code on Ubuntu, Linux. I do not have Windows, so I can't test it, but theoretically it should work or work with minimal changes. Yeah, and how I will organize these videos, I will write the small amount of code, try to explain what this code does, and the most importantly, why it does that. So the plans are to make multiple videos because the amount of information is just huge. It can't fit into one video. And unfortunately, maybe it's not what you expected, the mesh shaders themselves, you will write not soon. So the first thing is to prepare the Vulkan, the surface for the rendering, and some GUI, because it's much easier than you have some visual knobs and sliders to do something. And only after this, we can start to do some cool stuff. But the good news is I will use the same framework for probably next videos. For the next topics, I'm not sure if I will do them at all. A disclaimer, I'm not a professional YouTube blogger, and I'm still learning. And probably there have been many errors in both recording video and how I explain certain stuff. So just give me some time. And if you have some thoughts how to make these videos better, just write down. Yeah, that's basically it. So without further ado, I'm just putting my Vulkan head and let's start coding. So as promised, I'm starting completely from scratch. So here I have Visual Studio Code, empty project. Currently it has nothing. I created a profile for Vulkan, but currently I have nothing related to it. So I do not have any extensions besides this pre-installed compiler thing, which by the way I disabled. So we will not use any AI assistant tools. So this will be, as mentioned, completely old style programming by hand, so on. So I just created a dummy project of dummy repository for this project. So let's just clone it. And yeah, let's open this folder in Visual Studio Code. You can see nothing exists here. So yeah, the first step would be to set up all the necessary tools. So as you see, we will use Visual Studio Code for this, and we need some extensions to work with C++. So yeah, as a first step, let's just install these tools. And the first tool we absolutely need is Microsoft's C++ extension pack, I believe. So it has auto-completion for C++ code, and it has CMakeTools. Basically all we need. I think this should be enough for our project. As we go, maybe we will discover we need more. So we will install the necessary tools, but yeah, so this is the bare minimum you need, and I think it's installed, right? Yeah, so we have CMake, C++, so yeah, as you see, as you already guessed, we will use CMake as our build tool for our project. So basically, yeah, we will write a lot of CMake code, and of course C++. Also, I have to say about Vulkan SDK, so when you develop a Vulkan application, you absolutely need an SDK, and this is up to you how you install this. Currently, at the moment of recording this episode for this video, I'm still on Ubuntu 20, I think. Let me check. Yes, I forgot actually. Yeah, it's Ubuntu 20. And I didn't install SDK, so instead I'm just downloading the tar package from the LunarG website and just follow the instructions, sourcing basically the paths and everything, so we can check which version I have right now. VK config. This is a super amazing tool. We will use a lot this tool as we go. So here it tells like I have outdated version, but I have the latest version 3.2.8, but yeah, so I didn't have this minor patch, so that's good. So yeah, so let's see, I have how to check. Yeah, so this is the version 3.2.8. So at the moment of recording this, as mentioned, the latest SDK, I have this on my machine, and you need to install this too. Just follow the LunarG documentation for your system. And yeah, so first let's just build the skeleton for the application, just the general folder structure and some main C++ function with a hello world text. And after this we can start. Okay, so before trying to compile, let me set up the Visual Studio Code. Usually I prefer to have white spaces rendered. So since I just created a new profile, so it doesn't preserve what I have in other profiles. I think it's called white spaces. Yeah, render white spaces. So I just like to see all the indentations and everything. Yeah, so let's just start. I have C++ main CPP function, so currently, as you can see, it does nothing, just printing hello world and exits. And as mentioned multiple times, we will use CMake to build the application. I have CMake, let me check, I have 3.31 version, but I think so we need 3.25 because some variables were introduced in this version which we need, so maybe as we go we will see what exactly needed. If I remember, then I will show in documentation why exactly this version. So yeah, I highly recommend to follow and use at least this version, so you have the newer version. Yeah, I'm happy for you, just continue to use it. So here, yeah, I will try to explain every line of code, so this is how we will do this. As I explained before, so I will write some code, basically live, so then I have a pause explaining what's happening exactly. So as you can see, so this is our CMake list file, like it's not the main CMake because CMake main this here, but yeah, this relates to our application project. As you can see, we have multiple folders, so app folder is where our main executable will live. Like the teapot will be the name of the executable. Also we will have libs, like in this folder we will put everything which is not related to the main, but for example the graphics lib, which will be responsible for graphics. For third party we will use some third party libraries, and for this the main CMake list will just orchestrate everything. But yeah, let's look currently at the application CMake list. We call project teapot for this project. Yeah, we can have multiple projects in the executable folder, but we will have only one. So the executable with this name. Currently only one source file here. And we will use C++ 17. Why? Simply because I am on Ubuntu 20. And I have this quite old GCC compiler, so unfortunately to use C++ 17 maximum, I'm too lazy to install the newer Ubuntu. Maybe as we go, maybe I will upgrade my system and install, and then I will upgrade the version as well. But as for today, let it be C++ 17. Yeah, so required standard, no extensions. And yeah, we need here to specify the language. C++, of course. Let's copy this line. And we just do add subdirectory to our main application. I think as I hit up Control Save, CMake will detect the changes and will configure the project. No, it didn't happen. I think that's because we never ran CMake by itself. That's why it doesn't know something exists. So we can go here in the CMake extension, then project outline, and reconfigure the projects. So here it will ask which compiler to use. Yeah, so by the way, I have 11. I don't remember when I get this, but doesn't matter. So unspecified, so let CMake decide what we'll use. Yeah, so now we configured the project. Now we can build it. We can build it just hitting this build button with CMake, and it immediately complains. Yeah, because main, of course, main should return something. So we can build the project, so it automatically goes to the build directory. Of course, you can set up whatever you want, settings for the extensions. But yeah, normally it goes to the build directory and then try to follow the directory structure. And now it's in this folder and we can run it. Hello world. Yeah, and one more important thing. So not usually, like always, I'm adding a file for automatic code formatting. So in this case, we will use clang-format tool. I will just copy paste it from one of my existing projects. So it's basically how the code will be formatted, so everything looks the same. So for example, if I just do something like this and hit Ctrl S, nothing works. Let me figure out why. Because normally the Visual Studio Code should detect this clang format file and should use it for code formatting. Normally it should format this on Control Save, so probably that's somewhere in the settings. So let me search, where is it exactly? So I think I found this. So here what I mean by the clang format, so there is a setting for CPP extension, so it tells that we can use different styles, or if we use Word file here, then the style is loaded from the clang format file, which is here. Yeah, so it should use, but it doesn't use. Still, I think that's because so this format on save is turned off. I hope then I turn it on. It should work. Yeah, so now it works. You can see, so now if I do something crazy, stuff like this, and I hit Ctrl S, it almost did correctly. Yeah, so it works. Now, for some reason, it complains on something. I don't know, it's everything still works. Like this, like reload window is a super useful thing. It tries to reload the things. We need some time to wait. I don't know, everything looks fine. Sometimes it happens, I don't know why, but Visual Studio Code can't, for some reason, suddenly stops to detect some include file paths and start to show this red squiggles as you saw just now. I still don't know how to solve it, so it happens randomly. So let's check that still everything works. Super, good. So we are good to go. Now the next step before starting, we need to decide how we will bring third-party libraries here, because there are multiple ways how to do this in C++, and there is no official standard way how to do this. Everybody's doing by their own. For example, it can be Git submodules, it can be a Conan package manager or some other package managers. But for simplicity, here in this application we will use CMake fetch command. So yeah, it will get all the dependencies automatically It's maybe not super ideal, it has some flaws, but it works. It works, and it will for sure will work for this simple application. So first, let maybe start to introducing this tool by first getting the library for formatting. Yeah, this would be a good thing to begin with. Good, so this is how I will do in this application. So I have the folder for each dependency, which I put to third-party directory. So inside this folder, I will use git ignore because I don't want this dependency to go to my repository, obviously. So I want to keep it separate. And this is the rule which explains what to do and how to do. So again, the same version. So here, the version of the library and the library itself. I will use for formatting this amazing library called FMT. The latest tag is 12.1.0. So let's put here exactly like it's written here. 12.1.0. And the repository for this is this. So what this comment does. So this is not a part of vanilla CMake installation, but it's easy to get this by including this file. So this file comes with CMake, but it's simply not visible by default. So after this line, we can use this command. So what it does, it basically downloads the library from this repository and places this into this repository. So the source relative to this CMake we are looking at. So basically it will create a source directory here in this FMT folder. We'll put all dependencies there, and like this library is written very good, so it's aware about fetch content. So all we need to do is basically just make it available and everything will just work. That should be git tag. So now for this to work, we need to add this subdirectory with this library, and let me check what it is exactly. Yeah, so I just missed the closing mark here. Now we can either just reconfigure from the scratch or just go to our main CMake, just change it, save it, and as you can see, it started to download the library, so it finished quite fast. And if you look, we can see the source here. That's very good. So now we can add the dependency, this library, to our main application. Let's do it now. As you can see, this library was found by CMake. And this is the syntax, how they use it, how I know the name of the library. Well, yeah, it's written in documentation, or we can go, for example, in the source for this library and just try to find head library. Yeah, so this basically how I know the name. We can use either format or use this cool namespace name. Now we can use this, so I added the dependency to our main application, and now instead of this IO stream, we can use this library. It's the same as C++23 STD format. So basically in the future, maybe for me, then I will upgrade my compiler. So all I would need to do is to replace this FMT namespace with STD, and it will just work. So this library has a lot of cool formatting features, which we'll use a lot. But for now, let's build it. Let's run it to see that it still works. Very, very good. And one more thing is debugging. So let's set up the debugger for the application. Before, let's solve this problem. Currently, I see 108 changes for the library for this repo, and that's probably because the build directory is not excluded here. So we don't want to push the build directory. So let's just set here. Yeah, so 8 files. For debugger, we use Visual Studio, amazing tool. We create configuration, launch configuration, and we want touch. So let's call it T-pod, and let's specify the path. So that's the path for our executable relative to the workspace folder is like this folder. Yeah, the selected project with .vs code folder inside. I think that's enough. Wait, that's wrong. So it shouldn't be attach, it should be launch, right? Yeah, it should be launch. Let's remove all this. So the working directory will be... let the working directory be... let it be the directory of the binary itself. Yeah, so that's enough. We are not using any environment or arguments at the moment. So now, in theory, then I hit F5. We should hit this breakpoint. So I'm hitting F5. And it works. So yeah, we can see here, we can see the stack, the local variables, which we do not have currently. But yeah, we can examine the different registers. That's a very good start. Very good start. So we have a skeleton. Let's just add everything to repo. Initial commit, edit, FMT, dependency. Let's commit and let's push. Nice. So next, let's just do some again organization, like where should the code go, how should we proceed, and where actually to start. And we will start by adding our first dependencies to the libs folder. So we will organize the codes like this. All the graphics code will go to the graphics lib. Maybe there will be some util libraries or any other helper libraries. That's actually very good that I remembered. So the first library we will absolutely need is this library. So usually then I write the code, I am turning on the warnings as many as I can, and I'm treating warnings as errors. That's a very good practice, and I highly recommend to do the same. And actually, yeah, let's start with this library because we can already test it in the main function. I will not type this thing because this library, it just jumps from one project to another project, so I'm always using the same file, so the same like the version. Let's just add this thing, and here just the rules, the warnings we will use. It's for different compilers. In my case, it will be GCC compilers, which inherits the warnings from Clang. It's different stuff like unused variable, like shadowing, and you can read it if you want. Let's just format, because auto-formatting doesn't work for CMake, only for C++. And this will be a library, as you can see here, like this is the name of the library, and it's an interface library. So interface library in CMake is something which doesn't have a binary artifact, so it basically just the source code. For example, it can be header-only library, which obviously it's a header-only, so you can't build executable out of it. Or, for example, this library doesn't have any code at all, CPP or headers. It only has a CMake, but still it's a library which we will link to our different libraries, so that's why they have to be interface. And that's basically it, nothing special. Here we just add options, the build options, which are all this compiler option for warnings. Now we can link this lib to our application. And there's error. Let's check. That's because CMake doesn't know about this library. And this library lives here. Good, now it's linked. Now if you try to, for example, do like this is unused variable. If we build, we can see that the compiler detected that this variable is unused, and since I marked this thing as, I think this tells to treat all the warning as errors, here I get, instead of warning, I just get an error. So yeah, this will help to keep our code clean, and will guarantee that it will work on different machines, different compilers, different systems. Hopefully still not guaranteed, but the chance is much higher without this. So this was our first library. Now let's actually think what to do next. So usually I organize Vulkan code in this specific VK directory. That means that in theory this graphics folder can have VK, DirectX, OpenGL. Of course, we will not do this. But still, I just like to keep things clean, so we will use VK and all these namespaces. Yeah, so I added this graphics VK libraries. Inside the graphics I just put subdirectory which points to potentially again multiple versions of graphics API, but in this case we have only one. So here just the basic things. It complains that this library can't exist without sources, which we don't have at the moment. So let's just command these things. That's how it works. So let again summarize everything. So we have top level CMake, then we call CMake manually, for example, or with CMakeTools like here. The CMake will grab this file, will start to read it, start to add the necessary functions, add directories. Inside these directories it will read the corresponding CMake list files and build everything. We can actually see what exactly CMake is doing by looking at this compile commands thing. For example, here it builds a format, a library, and our main CPP. This is the file, and this the list of the different commands. I just want to find which configuration it runs, so I do not see here if it's debug or release. So normally there should be debug button to select the configuration. I don't quite understand why it doesn't exist at the moment. So maybe there is some setting. I need to check this out. But yeah, that's how it works. So if you wonder how to do without these tools, for example, we can execute CMake and basically it will do the same configuration for us. So this command just calls the configuration. So I'm currently inside the build directory. I need to specify the path to the main CMake file, which is one directory app. So from build directory to this file. And currently it doesn't do anything because there is already the build folder is not empty, it's configured. But yeah, that's the idea. If I want to build, I just do like this and I can build the target. But we will use the visual tools and IDE as a helper. Yeah, so let me figure out how to add the debug and release buttons. Okay, so I googled a bit and it changed apparently from what I used before, so maybe the version of CMakeTools changed. So now I need to run this command, select variant and for example debug. Still, that's strange because before I could do the same just looking here and know exactly which variant I'm using. Again, maybe there is a setting for this, but I couldn't find. But yes, okay, as you saw, I selected the debug variant, so I selected this, so it configured the project. Now let's look again here to just detect, did it actually use the debug version? Yeah, so it uses a debug version. And I do not see any optimization level, like 0, or 1, or 3, so I suppose this G is basically enough, so the flag tells the compiler to build a debug information. Let's actually see what happens if we select the release. Yeah, we can see that instead of G, it uses this all3 like for optimization. Let's return it back, and I don't know, I still need to figure out how to add these things here to the UI. But okay, so now we can start to actually talk about the Vulkan. The Vulkan is very complex API, and I can imagine the newcomers who just start to learn it could be just mind-blowing, like where do I start? That was exactly for me. And yeah, so I don't have any universal advice how to do this. I will just show how I usually start. Maybe you can learn something from me, or if you have some remarks, please write a comment. for this video, just to show how you're doing. Maybe it would be so good that I will adjust my code and use the new style. But anyway, here we go. And just a step back here, I think I found why I do not see a status bar here. It's because for some reason CMake hides it. So if you go to settings, search for the status and CMake, it shows hidden. We can have a compact or just let's make it visible. And now we can see the configurations. Here we can select between different. So for us to debug, I like then everything is on the screen. It doesn't clutter UI so much to remove it. But yeah, here we can select the target we want to build. Currently we have only two, the format library and our application. But let's build everything every time. Cpack, we don't need this. ActiveKit, no, you got the idea. Now I think we're finished with the setup. And we can finally talk about Vulkan and coding. Okay, so let's briefly see what's happening here. I added a new library. As you can see, the window library, the CMake file here, and the third-party dependency did exactly like for FMT library. Here I'm using the latest version 3.4 at the moment of recording. Yeah, so again, this Jellyfile library has a very well-written CMake list, so introducing this to our project with fetch content is as easy as just fetch content and declare, so it just works. I don't know why it says something's broken here, so we can ignore it. Then the window library itself, so here is the signature for this. It's pretty simple, so it's basically just a wrapper around the Jellyfile window. So here we keep the pointer. We need this width and height to track if the window was resized or not. So let's look at the implementation. So constructor does nothing, and anything here we just initialize the library itself. We check that if Vulkan supports it or not. So this library has some Vulkan support, so it will help a lot. Then we'll try to create a surface which is like looking a bit of ahead of time. It's a cross-platform thing, and it should be handled separately for different platforms. So this library helps by hiding this platform-dependent code from us. Then this flag tells that we are not going to use OpenGL, so we want to have window resizable. Then we just create the window, and we just set the minimum size to be this size and the maximum whatever is possible, so we don't care. The destroy function just destroys windows and closes the library. The get just returns the pointer. I don't remember if we need actually this to be pointer or it can be const pointer. So let's for now just make this get function const. And we return the const as well. If you'll find that some calls will require from us to have a non-const pointer, I don't know why, we will change this. But yeah, let's keep it like this. So the tick function. The idea of this library is you have to manually pull events for the window. So basically we will have an infinite loop in our main application, and during each iteration we have to ask the library to check which events were processed during this time between different loop iterations. And basically what it does, it just collects all the events and just raises some flag inside the library, so we can check, for example, if during one update, one iteration of the loop, you decided to close the window, so the flag will be raised, and then you just can request this property by explicitly asking for this. There are some things like callbacks. For example, I saw there is a resize callback, but we will not use it. It makes code a little bit complicated. Also, we want to have this property to know if the window minimized or not, so it's called iconified. So basically, we don't want to run any graphic or any work at all if the window is minimized, because why, right? And the size. So the size, I decided to return the size info. It returns the current width and height, and the property indicating if the window was resized since the last update. So here how it's done. I'm just requesting the current width and height from the library, and then I just check if this properties were changed since the last update. As I mentioned, we can use callback here, but callbacks are kind of global functions, so for this I need also to have some global properties for width and height. It's not worth it. I don't think we will have resize, which can happen many times per update. It can, theoretically. I'm just thinking about this right now. So if during one frame you can resize a window somehow, I don't know how, multiple times, the surface will be destroyed and you need to handle some special cases for this, but yeah, it's very unlikely you won't do this. So that's how it works. Basically, you check if the size was changed, maybe return the property saying that it was changed, and then in Vulkan code we have to handle this accordingly. Regarding these to-dos, just give me a moment, I will shortly say what's happened here. And the library we will use in our main applications, that's why I link it here. And in the main function, this is how it's called. Basically, we create a window, we initialize this, and that's what I was talking about. So in this infinite loop, we check while the window is not closed. We just continuously update it. So without this tick, we will not be able to detect if the window was closed because events were not polled and this closed flag will not be raised. Then it's closed, the loop will finish, and we will destroy the window. And if I build it, it builds okay. I can hit F5 and run it. So this is our window. We can resize it, we can close it. So it works. And now let's go back to this to-dos thing. In the very beginning, I told that on my machine I have a pretty old GCC version and G++ version with 10.5, and it relates to the thing which I want to discuss here now. So what should we do when we hit this kind of problem? So basically GLFA can't initialize or any other exceptions which we can't recover from. In this case, we just need to terminate. Here I possibly can call abort, but it's not elegant at all. Another thing is to just throw an exception like this. For example, it's fine, it works. A lot of code depends on exception things, but there are better, in my opinion, alternatives to this. So for example, why I don't like the throw thing. Not that I don't like it, as I mentioned, it worked perfectly, it worked for decades. But for example, if just imagine we have some function like, I don't know, let's call it full, which throws, for example, 32. What should happen? For example, then we call it from here. Here the function says it's non-accept thing. That means that if there is an exception inside, then abort will be called. And we can't catch basically something inside, and we can't even know the reason what was wrong. So let's say here is full and foo2, and each function can throw. We can use try catch here, but the thing is, what if I just later change function, or for example, this function full was no accept also, and it just return something. Yeah, it was fine, but later we decided, okay, this function actually can throw, and then we need to find every entrance of this function in our code and just use try catch block, and then if we change it later to something else, we need to do this. It's just a lot of code. And for example, for some third-party libraries, sometimes we don't have a source code, and we need to refer to documentation to find out if function can throw or not. In my practice, I saw a lot then even the well-known code, for example, doesn't document, but the function can throw, and yeah, that basically sucks. Another solution to this is just to use return codes, and that's also fine. It's like typical C API, I would say. But personally, I don't like it that we need to return some value, like for example here. And if the function should return the code result of the function, then we can't return something else here, and we need to rely on pass size info by reference or by pointer. That's also fine. That's basically how the entire Vulkan is made. But I would like to be more modern, and I would like to use more modern C++ features. And for this kind of thing, C++ 20 introduced expected data type. which basically returns something. And if this something has a value, we can get this value. If not, if this something has unexpected value, an error, then you can get the reason why it didn't return what we wanted. The thing is, we can force the compiler to not to ignore this value. So the situation with try catch, if you forget to wrap it in try catch block, it will be much difficult to forget. So if the function should return something and we force to not to ignore the return value, we have to check it. And if the value is expected, we have to check if there is something inside or not. So yeah, that was the decision. And we will use as the expected. But the thing is, if I will try to use it right now, it can't even find it because, as I mentioned, my GCC version is too old and I was just too lazy to update it. But just recently I found that I have multiple versions of GCC on my machine. I don't remember how I installed this, but yes, with my current version. But I have multiple versions, including GCC 13, which should support C++ 20 and expected thing. Oh, let's just update the version of GCC on my compiler, and if you follow me, then you need to do this too, and from now on we will target C++ 20. Okay, I told my system to use GCC newer version. Now it's 13. Let's just go and see what's happening when I change the signature of the functions and return the new data type instead. Okay, so yeah, I updated one signature for one function and tried to compile, and yeah, it says that C++ from 23. So yeah, it's not C++ 20, it should be C++ 23. So we just need to do it here. And yeah, so I need probably to clear the complete build folder. Yeah, it starts to download thing. Yeah, the thing with fetch content thing, it always tries to search the dependencies on the web. So if you don't have a connection, you will have problems, so it will not run. So there are a couple solutions to this. First, to detect if the dependencies are indeed exist. So here we have third party, we know exactly where to search them. If they exist, then just skip fetch content thing. Here, for example, we can make CMake check. So if source is not empty, then that means we already did the thing. But I will not do this in this case. Yeah, but now I see that the configuration step succeeded. And now I can try to build. Yeah, no, that's my typo. Yeah, and here it complains that since the main function includes window and this project uses 17, so it complains. So we need to change the standards for every project. Let's do it. So far so good. Now it compiles, so we are using C++ 23, the expected works. And let me check if I commented everything here right. So yeah, for any expected thing in this project, I will use just a string indicating the error type. So this would be for any function, any class in our application. So the return type, the expected thing, of course, will be different, but the error always will be a std string. One thing I mentioned, so not to forget to test it, we will add this thing. That means we can't and we shouldn't ignore the result of this function. So for example, if you look, we just calling it, but we do not check result. Now if you try to compile, it just says trying to ignore the value which should not be ignored. Let's quickly fix it. Excellent, so it works now, but you may ask, okay, now since this thing returns expected and we need to wrap each and every call into this structure just to check it, and the answer is yes. So basically we have to do this. For example, in Rust they have a special question mark operator which just expands this automatically, and for example if you call a function which returns also expected, like in Rust's case it's different, it's result, but in our case it's expected. So if you would use this question mark operator, for example here instead, then it would expand this automatically. So if the result is a success, we will continue execution. If the result has an error, it will be propagated. So if this function will return as expected, but string as an error, then this call will automatically return this thing. But yeah, we are not writing in Rust, we are writing in C++. In C++ this doesn't exist, but we can simulate this kind of thing. I'd suggest to write a macro function which will replace basically these multiple lines with one line, just to make code smaller and easier to read, because we will have a lot of this pattern, just a lot. All the function which can fail will return expected, and if you just put if else everywhere, oh, it will just blow all the code. And here, for example, init returns void, but just imagine it doesn't return void and return some other value and they need to store it. Yeah, it's just a lot more boilerplate code. So let's write a macro. And since we will need this macro basically everywhere in the project where we use expected, we'll put this macro in another library. So let's make some utils library and keep stuff like this macro and maybe some other stuff there. Okay, let's see what we've done here. As mentioned, I created a library. In this case, it's just a single header file. That's why the library have to be interfaced, because the library doesn't produce any artifacts, no binaries, libraries, nothing. It basically just propagates whatever is inside this library. In this case, just a single header. I call this library utils with alias libut. I added this library to the project subdirectory. Then I linked this library to our main. The library itself for this macro, how does it work? So if you look here, how we call it, so basically we just provide the expression. In this case, the expression is window init. So it propagates here, then it creates some variable with a random name. Oh, I think I forgot something here. Let me add it here. Yep, so this init function will be typo again, be passed here, so here it will just stay init. And this counter is a special macro variable which will be expanded to some random, which will increment every time you call it. So the first time it will be 0 probably, then 1, 2, 3, and so on. This is necessary because in one file, just imagine here, we have multiple calls to this macro, and then it tries to create a temporary variable, so we want it to be different, to have different names. In this case, this thing will be expanded to TMP 0 or 1 or 2, and then it will assign the result of expression. In our case, it's window init. Then it checks if the window didn't have success. Then it will just propagate this error, basically returning here. So in this case, the execution will stop here if there is an error, and return the expected. Here in this case, expected will be unexpected. So here how it's created. If the result was okay, then this thing will not be executed and will propagate further. This is one implementation for the void function like our init, but I probably will need another implementation for function which returns expected, which is not a void. Yeah, it's a little bit ugly, but unfortunately that's what we have. There are better solutions, for example GCC and Clang, they have extension which we can use in more elegant way. I don't remember exactly how, but it's not a standard, so it's just extension to a compiler. I want to stay in this project purely in standard C++, so that's why I added this. No extensions, I think. It compiles now, and let's see if it works. It works. Maybe let's check what happens if this init function returns something wrong. First, let's try hit F5 to see if we can follow the next lines, because everything is okay. But if we just change it here to something like this, recompile it, then I expect this should return immediately here and put it here. Yes, so that what happens. It prints the result of our error, and that's how we handle the exceptions in our application, and we will do this for basically everything. So in case we can't recover from the exception, we just print the reason and exit the application. Yeah, and I think that's it for this first introduction video. As mentioned, no single word about Vulkan, unfortunately, but at least we prepared the ground, the solid ground, I would say, for our application. Let me push everything to the repo. In the next video, we will start to explore Vulkan. So again, we have everything to start. So the window is here, the surface to render, and yeah, we will incrementally go step by step to finally see our beautiful mesh shader. Okay, see you next time.